I'm tackling a dimensionality reduction problem. I have a massive dataset, 1 million user website interactions, each described by 10,000 features, website pages, that I'm trying to simplify. My goal is to reduce this to just 50 key components. This is a large, sparse dataset. Many entries are zero. I'm working with a really big and sparse dataset. Think of it like a giant spreadsheet. 1 million rows, users, 10,000 columns, website pages. And most of the entries are zero, representing a lack of interaction between users and pages. This sparsity needs a special algorithm. I want to boil down those 10,000 website page features down to only 50 principal components that still capture most of the important information about user interactions. I'll use sparse principal components analysis, SparsePCA, to solve this. It's a special type of PCA that's great for sparse data like mine. That's because it's designed to deal with datasets where many entries are zero. If I reduce the number of components to only 10, the calculations will be much faster. However, I risk losing important information. It's a trade-off between speed and accuracy. SparsePCA is perfect for my problem because it's specifically designed to efficiently handle high-dimensional data that's sparse, lots of zeros. Standard PCA would struggle with this dataset. Increasing the alpha parameter in SparsePCA actually makes the resulting components sparser asterisk, not denser. Alpha controls how many zeros are in the final components. Unlike regular PCA, SparsePCA doesn't guarantee that the resulting components will be perfectly orthogonal, meaning they are completely independent of each other. It prioritizes sparsity over strict orthogonality. The whole problem revolves around applying SparsePCA. I'm testing my understanding of how SparsePCA works and how its parameters affect the outcome. I'm using SparsePCA, a powerful algorithm from the Sklearn library, to shrink the size of a large dataset. It's like taking a massive photo and creating a smaller, clearer version without losing too much detail. Imagine a website with 10,000 pages, and we have data on how 1 million users interacted with them. That's a lot of data. SparsePCA helps me deal with this size. I'm aiming to reduce the dataset's dimensions from 10,000 down to just 50. Think of this like summarizing a long novel into 50 key points. This is the goal, to make the data easier to work with by greatly reducing the number of variables. It's crucial to reduce dimension while still keeping important patterns. If I choose a smaller number of components, like 10 instead of 50, the process speeds up. But I risk losing some important information. It's a balance, like choosing between a quick summary and a detailed review. SparsePCA is specially designed for datasets with lots of zeros, like mine. It's much more efficient than other methods for such data. It's like having a special tool for a special job. The alpha parameter controls how sparse, how many zeros are there. The results are. A larger alpha creates sparser results, more zeros. It's like controlling the detail level in a compressed image. Higher alpha equals less detail. Standard PCA makes sure components are mathematically independent, orthogonal. SparsePCA, however, prioritizes sparsity over strict orthogonality, but that's okay. I'm using SparsePCA, a PCA algorithm designed for sparse data, to reduce the dimensions of a large dataset. This is perfect for my user interaction data because it is very sparse. I have a massive dataset, representing 1 million users interacting with 10,000 website pages. Importantly, this dataset is sparse, meaning most user page interactions are zero. A user didn't visit that page. I'm using SparsePCA to reduce the dimensionality from 10,000 features to just 50. The _n_ components parameter dictates this target dimensionality reduction. I'm asking you to evaluate 4 statements about how well SparsePCA is suited to my problem and how its parameters affect the results. My goal is to reduce the number of features to 50, making my data easier to work with. This is a form of dimensionality reduction. This question tests your understanding of the SparsePCA algorithm in the Sklearn library and how its hyperparameters affect its performance on high-dimensional sparse data. I'll need to carefully consider each statement provided. This is true. A smaller number of components means less computation. However, if you reduce the number of components too much, you're likely to lose crucial information from your dataset. Think of it like summarizing a book. A shorter summary is quicker to write, but you'll probably lose some details. This statement is also true. SparsePCA is specifically designed to work efficiently with large datasets containing many zeros, which is exactly the type of data described here. Standard PCA would struggle with such a dataset. I think of it as having a toolbox. SparsePCA is the right tool for this job. This is false. The ALPHA parameter controls the sparsity of the components. A higher ALPHA value actually makes components sparser, more zero values. This is false. Unlike standard PCA, SparsePCA does not guarantee that the resulting components are orthogonal, meaning they are at right angles to each other in the data space. The focus is on sparsity, so orthogonality is often sacrificed for that benefit. We have a massive dataset, 1 million samples, like users, and 10,000 features, representing website pages. The key is that this dataset is sparse. It contains lots of zeros, which means most users only interact with a small fraction of the web pages. I am using SparsePCA, a technique for dimensionality reduction. The goal here is to reduce the number of features from 10,000 down to 50, while preserving as much important information as possible. The number 50 is the target number of components, principal components. After applying SparsePCA, the result will be a reduced dataset with only 50 components instead of the original 10,000 features. These 50 components will capture the most important variations in the data. NCOMPONENTS is a hyperparameter that controls the number of principal components retained after dimensionality reduction. It is directly related to the computational cost and information loss trade-off. Alpha is another hyperparameter. This one controls the sparsity of the components generated by the algorithm. A higher ALPHA value will yield sparser components, more near zero values, while a lower value leads to denser components. I'm using SparsePCA, a technique from the Sklearn library, to shrink the size of my data while keeping important information. It's perfect for dealing with datasets that have lots of zeros, like the one I'm working with. My data is huge. I have 1 million user samples and 10,000 features representing web pages. It's sparse, meaning there are many zeros. Think of it like a really large, mostly empty spreadsheet. This just reiterates the massive size of my dataset. 1 million users interacted with 10,000 web pages. That's a lot of data. I'm using _n_components to control how much I shrink the data. I want 50 components. The _alpha parameter tunes the sparsity, how many zeros there will be, of the result. _n_components equals 50 means I'm aiming for a 50-dimensional representation of the original 10,000-dimensional data. _alpha is a hyperparameter that controls how sparse the components will be. A larger alpha means sparser components, more zeros. I'm testing your understanding of SparsePCA using multiple-choice questions. This is the core question. Which statements accurately describe SparsePCA and how it's used in this scenario? This statement is true because fewer components mean less computation but possibly some loss of detail. Absolutely correct. SparsePCA is designed to handle massive datasets with lots of zeros, which is exactly what I have. This is false. A larger _alpha makes the components sparser, more zeros. Nope. Unlike standard PCA, SparsePCA does not guarantee orthogonal components. The goal is to reduce the dimensionality of the data from 10,000 to 50, preserving as much important information as possible. The result is a transformed dataset with fewer dimensions, 50 instead of 10,000, suitable for further analysis. I'm using the SparsePCA algorithm, a tool from the Sklearn library, to shrink the size of a large dataset. It's like taking a giant photo and making a smaller version that keeps the important details. I have a massive dataset showing how users interact with a website. Think of it as a spreadsheet with 1 million rows, each representing a user, and 10,000 columns, each representing a website page. This is a really huge dataset, making it challenging to work with directly. The dataset's size is enormous. 1 million users and 10,000 features, website pages they visited. This is a key challenge. I need a clever way to handle this. I'm using Sparse Principal Components Analysis, SparsePCA, which is provided by the Sklearn library in Python. It's a special type of dimensionality reduction that's great for large datasets with lots of zero values, sparse data. I want to reduce the number of features from 10,000 to just 50. The parameter _n_components in SparsePCA controls this. It's like summarizing a long story with only 50 keywords. The goal is to create a smaller, more manageable dataset with only 50 components, features, while still keeping the most important information. Think of this as a smaller, more manageable version of the original dataset. I'm answering some questions about SparsePCA and how it handles the dataset. This is a multiple-choice quiz to test my understanding. This is a multiple-choice question evaluating my understanding of how SparsePCA works in this context.